Greetings to all. In this lecture, we will discuss the equations for bar resistance and end ring resistance, because the slip ring induction motor is nothing but the cage, right. Okay. So, for cage, how to find the resistance value we will discuss in this lecture. Okay. Let us take the resistance for a single bar which we have already discussed. Okay. Resistance of the single bar, that is RB, is equals to resistivity of the bar material, whether it may be aluminum or copper, that is resistivity of the bar material, length of a single bar divided by area of the cross sectional area of the each bar. Okay. This is in the ohms, equation number 1 to find the bar resistance. Single bar we have discussed. Now, in the last lecture we have discussed the skewing of the rotor bar, right. This is the actual bar length, that is LE, without any skewing. Now, if we will skew the rotor bar, then the length of the bar will definitely increase, right. If we will consider it as a right angle triangle, and skewing angle will be alpha, where alpha is equals to skew angle, which is equals to 2 pi by qs is nothing but slot angle in with respect to the mechanical aspect, into p by 2 will give the electrical angle, into SSQ will give the how many slots we are skewing, alpha equals to this one, and LE we know, and length of the actual bar with skewing we have to calculate. Then as per the trigonometric equations, length of the skewed bar is equals to LE divided by cos alpha. Okay. Alpha we know, that is 2 pi by qs into p by 2 into SSQ. By substituting the alpha value and LE value, then we can find the length of a bar, skewed bar. Okay. After knowing the length of skewed bar, we have to find the end ring resistance also. Okay. If we will see the rotor mesh is nothing but combination of resistance and inductance values. Okay. Like this, it will be n number of bars are there, and end ring also there, 2 end rings will be there, circular end rings. We can see here, this is one end ring, one side, and other side one more end ring is there. The rotor structure I am showing here. Okay. This is the resistance of the bar will be RB, inductance of the bar will be LB. Sorry, these things are the end rings one, RE and LE. RE and LE. And resistance of the bar with after skewing, it will be RB, and inductance will be LB. Okay. Current flowing through the branch 1, let us consider this is the branch 1, that is IB1, and branch 2 is IB2, and current flowing here is IE1 in the end ring. In this branch also IE1, and this is IE0. Okay. In order to find the equivalent resistance for the rotor mesh, first we have to know the value of the resistance of the each skewed bar and resistance of the each end ring. So, we will calculate the resistance of the end ring first. that is Re. Resistance of the end ring Re is equals to resistivity of the end ring material into length of the end ring divided by area of cross section of the end ring. Okay. In the previous lectures we have discussed the and we have calculated the cross sectional area of the end ring also we know, and length of the end ring we can calculate it by doing the mean length. Let us consider this is the end ring. Okay. The depth will be dE and thickness will be TER. Okay. So, in order to find the mean length of the end ring, we have to take the outer diameter of the rotor, that is d naught r, and inner diameter with respect to the end ring by considering dc. Okay. So, inner diameter by considering dc will be d naught r minus 2 into dc. Okay. So, from here we can calculate the mean length of the end ring LER equals to pi into d naught r minus 2 dc plus pi into outer diameter of the rotor, right, that is d naught r by 2. It will result in pi into d naught r minus dc dcr, depth of the back iron. So, this equation will give the length of the mean length of the end ring. By substituting mean length here and the resistivity as well as cross sectional area of the end ring, then we can get the bar end ring resistance. Already we have calculated the bar resistance, and now we have calculated the end ring resistance also by utilizing this equation. Okay. By substituting Rb value and Re here, and from this network we have to find the effective resistance for the rotor mesh and effective inductance for the rotor mesh. Okay. For that, apply a KVL for this loop. Okay. This is the loop we can consider. Okay. For this loop, apply a KVL equation. Take the voltage E1 back EMF with respect to the branch 1, that is EB1 minus EB2, which is equals to RB into IB1 minus IB2, other branch resistance current also I am considering, plus 2 into and 2 times the end ring resistance are there, right, this side and this side, 2 Re into IE1 plus LdI by dt terms should come, right, LB into DIB1 minus IB2 divided by dt plus 2 times inductance with respect to the end ring into DIE1 by dt. This is equation number 4. Just apply a KVL with respect to the mesh which I have represented here with blue color. Apply that KVL equation and then we will see this equation. And IB1 plus IE0 is equals to IE1 from the above figure. So, in steady state, okay, the phasor form of the voltages and currents, okay, how we can represent the phasor form of the voltages and currents like EB1, EB2 and IB1 and IB2 are, okay. So, the EB1 is nothing but induced EMF with respect to the bar 2 and EB2 is nothing but induced EMF with respect to the bar 2 and EB1 is the induced EMF with respect to the bar 1. Okay. EB2 we can represent in terms of EB1, that is EB1 into some phase shift e power j theta, right. Here theta is nothing but phase or bar angle, that is equals to 2 pi by q r with respect to the mechanical displacement into p by 2 will give the electrical angle conversion. Okay. So, e power j theta we can mention here EB1 into e power j into pi into p by qr. This is the EB2 equation, equation number 5. And in the same manner, if we will represent the IB2 is equals to IB1 into some phase shift with respect to the phasor form e power j pi into p by qr. This is equation number 6. Same way, the current in end rings IE1 is equals to IE naught IE1 is equals to IE naught into e power j pi into p divided by qr. This is the phase shift. In these three equations, what I have done is I am representing the voltages and currents in a phasor form, where the phase shift angle between one value to other value like EB1 and EB2 difference is the angle theta. In phasor form e power j theta I am adding for EB1 to get the EB2 value. So, by substituting all these equations in the above KVL equation, that is equation number 4, okay, EB1 minus EB2, IE1 minus IE2 we have to calculate first. First we will calculate the EB1 minus EB2 is equals to EB1 into 1 minus e power j pi into p by qr, right. Similarly, IB1 minus IB2 is equals to IB1 into 1 minus e power j into pi into number of poles by qr. This is equation number 8, equation number 9, and with respect to the end ring currents IE1 is equals to IE naught plus IB1, right. Here IB1 is equals to IE naught, sorry, IE1 minus IE naught, that is equals to IE1 current in end ring 1 into 1 minus e power j pi into p by qr. Okay. So, from this equation we can find IE1 is equals to IB1 divided by 1 minus e power j into pi p by qr. This is equation number 10. By substituting equation number 8, 9, 10 in the KVL equation, we can get the EB1 equation, like EB1 is equals to EB1 into 1 minus e power j pi into p by qr is equals to IB1 into 1 minus e power j pi into p by qr, the term will be there, into r plus rb plus j omega l into b, okay, plus 2 into IB1 divided by 1 minus e power minus j into pi p by qs. into Re plus j omega Le. In the end ring current waveform, in the end ring current equation, IE1 is equals to IB1 divided by 1 minus e power minus j should come. Yeah, here itself it will be minus, because IE1 minus IE0 we are doing, right. Because of that thing it will come IE1 into 1 minus e power minus j into pi into p by qr. Okay. By substituting all equations 8, 9, 10 in the equation number 3, then we will get this equation number 11. After solving this equation by rearranging the terms, then we will get EB1 is equals to, in the form of IB1 into RB plus j omega L into B plus IB1 into Re plus j omega Le divided by 2 into sine square pi into P divided by QR. Sine square by 2 into sine square pi into P by QR, we will get it. I am not deriving in between steps, you just rearrange the terms here and then find the equation in this fashion. Then by equating the real and imaginary terms, RB effective resistance of the bar, effective resistance of the bar is equals to RB plus Re divided by 2 into sine square pi into P by QR. This is the effective resistance of a bar. Now to find the equivalent resistance per rotor mesh, that is RR is equals to 2 into RBE, 2 times the effective resistance of the each bar of the rotor we will consider, and we can find the rotor resistance per mesh. Okay. This is the final equation to calculate the rotor resistance. Similarly, inductance terms also we can calculate it. While discussing the inductance equations, we can recall the same equations and we can find the inductance values at that time. For in this lecture we will focus only with related to the rotor resistance. That resistance equation is the equation number 12. Okay. After knowing the rotor resistance, we will find the weight of the rotor cage. Okay. Rotor cage with respect to the winding, cage winding. Okay. So weight is equals to density into volume. Here density with respect to the aluminum we have to calculate, or copper we can consider, that is density into volume is equals to NR, the number of rotor bars, into length of each bar into area of cross section of each bar, plus 2 into length of end rings into area of cross section of each end ring. Okay, because 2 end rings are there and n number of rotor bars are there, because of that reason NR into L into area of cross section. Here 2 end rings are there, because of that reason 2 into LE into AER we are doing. The total thing we can get it, the weight of the rotor cage winding, that is equation number 13. Now in order to calculate the inner diameter of the rotor, okay, dir is equals to, we know the outer diameter, minus 2 into the slot opening height, that is d naught r, plus radius at the slot upper side, and slot depth dsr, and radius at the bottom side of the rotor slot, and the back iron width. This equation will give the rotor inner diameter. This rotor inner diameter we can calculate from the output function equations also, where we have to calculate the lambda 2 is equals to dir divided by d naught r, where the function f of copper function f of lambda 2, fr of lambda 2 and f naught of lambda 2 has to be maximized. Based on this thing we can find the lambda 2 value. Once we know the lambda 2, then we can find the dir value also, otherwise we have to follow this equation number 14. Okay. If we will follow the sizing equations, then we have to utilize the copper function with respect to the rotor geometry and output function with respect to the rotor geometry we can calculate, and then associated lambda value we take it and calculate the inner diameter of the rotor. Finally, the area of the rotor slot should be greater than the bar area, okay, or cross sectional area of the each bar. If it is winding, like slip ring induction motor is there, where the windings are there, AR should be greater than the number of turns per slot into cross sectional area of the each conductor. With this equation we can verify the window area with respect to the each slot of the rotor. So, with this I am concluding this lecture. In this lecture we have discussed the bar resistance with respect to the skewed rotor and end ring resistance, and final cage structure of the rotor mesh resistance also, equivalent resistance we have calculated, and rotor inner diameter and window check equations we have discussed. With this, complete rotor geometry with respect to the dimensions, with respect to the windings like rotor bars, resistance, weight, volume and everything we have calculated. Thank you.